Now let's discuss how this program is loaded and how this user mode address space is used, because we are going to discuss user mode internals. So again, we have the address space here. This is the entire address space. Like I mentioned, the first 2 GB is user mode and lower is kernel mode. And we have our application here, the exe file. This exe file is sitting inside the disk inside file system. It is not yet in the memory. So the operating system has created an address space like this. Address space is ready. Now, next thing the operating system does is map this binary. This binary is inside the disk right now. Let me draw that disk. This is the disk of the system, hard disk. So it is in the hard disk inside the file system. It's a file right now, just like any other file. When you double click or start the program somehow from start menu or somewhere, or even Visual Studio for debugging, or even Windbg, somehow you're starting the program either from debugger or some other way. The first thing it does is creating this address space, which is done. The second thing it does is map that binary into the address space. The binary is getting mapped into the address space. It is pretty much a ditto copy. There are some changes which are done based on how busy the address space is. I'm not going to discuss such details here, but mostly the entire binary is mapped into the address space. When I say mapping, you can think of it like the entire data is getting copied into the memory location here. Also, this locations, so this pink locations here are getting allocated, which means that it'll have a backup in the RAM. We have the RAM here, so let me draw the RAM. This is the RAM. Say I have 2 GB RAM, so 2 GB RAM. This is the RAM chip inside the computer, the random access memory, the physical RAM. This will have a corresponding entity inside the RAM. This binary will get loaded into the address space and it will have a corresponding entity into the RAM. Here, this address is called virtual address. This address inside the RAM is called physical address. I'll explain what is the relation between virtual address and physical address. Now, once the mapping is done, the operating system will start executing the instruction from this binary one by one. That is what happens when you start the executable. So it creates an address space, map the binary into the address space, and start executing the main. That is how it works. And this is inside the user mode. Now let's discuss the relation between the virtual address and physical address. So we discussed that the address inside the address space or the virtual address space, it is also called virtual address space because it has virtual addresses. Then the addresses inside the RAM, they are totally different. Let's see what is the relation between them. Again, we have the address space of the application here. This is the user mode, and this is the kernel mode. This is the unprivileged mode, and this is the privileged mode. We have the RAM here, random access memory. Let's see that. This entire address space is 4 GB. This is upper 2 GB. And this is lower 2 GB. This upper and lower is relative. In my case, from this diagram, the upper is user mode and lower is kernel mode. If you talk from the address perspective, the higher address is kernel mode and lower address is user mode. So it doesn't really matter. We say upper or lower. In this case, this is a user mode, which is 0 to 7 follows 7FF. And the kernel mode address starts from 8 follows 7 zeros and 8FF. Those are the ranges we are looking at. Now we have the RAM here. Say RAM is 2 GB. At this point, there is no allocation at all in this address space. The address space is completely empty, which means that it has no relation whatsoever with the RAM, which means that there is no usable space inside the address space at the moment. Let's forget about kernel mode for the time being. We are discussing about user mode. We have seen that mapping a binary which had a presence in the RAM. Like that, any allocation you are doing inside the user mode, inside your application, your thread stack, the local variables, which is always in this stack, arguments passed, everything is in the stack. We have seen that. Then the heap, the memory you allocate by malloc, heap memory, the NT heap, CRT heap, any heap. Then the global variables, static vars, all are going into this address space. Stack, heap, everything is going to this address space. Whenever you allocate any of this kind of usable locations, there will be a mapping created in the page table. Let me draw the page table here. This is the page table. Page table has primarily 3 columns, so it is a table. So it has 3 columns. The first column is the virtual address. Next column is the physical address, and there are some flags. This is how the layout of the page table. In fact, it is organized as a B tree, and the root of the tree inside a register called CR3. Let me draw that. This is the CPU right here. And CPU has a lot of registers. Along with that, one register is important for our discussion, which is the CR3 register, CR3. CR3 register point to the page table. And page table has virtual to physical address translation. That is the purpose of page table, PT. This one entry inside the page table is called page table entry, or PTE. This is a page table entry. What is a page? Page is a convenience to reduce the number of entries into this particular table. We have total 2 GB user mode and 2 GB kernel mode. If we start having page table entry for each and every address in this 2 GB, the page table will be too big. The search will be too difficult. There will be so many entries. What they have done is they have divided the entire address space into pages. And each page has an entry inside the page table, provided there is allocation for it. All right. In this particular case, if I'm doing an malloc and I'm getting a particular page, so this is a page, each square is a page, it is getting allocated. I have allocated, so that's why I'm shading it. This particular page inside this address space is allocated, which means that I got a new entry inside the page table. I called malloc for a size of, say, for example, 4K. Then I got a new page allocated. There is a new page table entry created. Page table for a particular process is unique to that particular process, which means that every process has a CR3 register. So we will discuss about switching the process context. Coming back to pages, whenever we have a valid allocation, we have a page table entry. There are APIs to do the allocation. Virtual alloc is the father of all the allocations in user mode. malloc, heap alloc, every allocation API, doesn't matter which programming language you're using, as long as it runs on Windows in user mode, it calls NT allocate virtual memory or virtual alloc. What virtual alloc does is, so it creates other entries like virtual address, descriptors, etc. So we are not going to discuss that. Our focus is on page table, which is the most important fact when it comes to virtual memory. You are executing an instruction called move EAX, dword PTR, then an address, and that address, this address, whatever this address, 0x some address, if that address is coming from one of these pages are not allocated. I don't have any page table entry. So what happens? I'm just touching the space. I don't have any valid allocation. Then I will get an access violation. That is what we call access violation. We will see that. Or in our layman terms, we call null pointer exception. Whenever we touch a null pointer or a page which is not having a valid page table entry, we will get this exception. We will see that. That is our first scenario. We're going to look at the crash, simple crash. What happens if this address is from, so I did an malloc. In fact, virtual alloc is a better word, so I'm going with malloc in this case. So I did an malloc here and I got a valid page. This is a valid page, so this is why it is shaded. So it is a valid page, which means that if I do a move EAX dword PTR, so this is PTR, then what happens is the processor, the CPU, will start something called address translation. What is an address translation? Address translation is finding out the corresponding page table entry for this particular page. So there is an entry for that particular page. That's why it's a valid page. That's why it's shaded. Yeah, we have done allocation. So we previously put PT into this page table entry and find out the physical address allocated for that. There is a physical address. And from that physical address, you will be pointed to a page inside the RAM. It could be RAM or page file. I'm not going to discuss the details of all page fault and stuff like that. Let's assume that there is no page file and everything is in the memory. So ace of the discussion, we are assuming that. Now, what happened? So we executed an instruction, move EAX dword PTR 0x12345678, and 12345678 is coming from this particular page. I didn't discuss the size of the page by purpose because the size of the page varies. Normally the size of the page is 4K in user mode in 32-bit, but it is different for 64-bit, and some of the kernel pages are bigger than 4K. Let's assume that all the pages are 4K. This address we are talking is 0x12345678. So that is the address we are trying here. We are trying to read. So this is a read instruction. What this instruction does, it'll try to read from this particular memory location and try to load that value into EAX. That is what this instruction is supposed to do, provided this particular address is a valid address. This is as simple as C equal to star PTR. Int C equal to star PTR. If you want to think from a C perspective, while PTR is a valid pointer variable which has a valid address inside it. So same instruction here, move EAX dword PTR, then this particular address 0x12345678. Now that address is inside this page, and this page has a valid page table entry inside the page table. There is an address translation happens. This could be anything. This address could be anything. So you have 2 GB RAM. So it could be 11223344. Anything. It doesn't even need to be a 32-bit address. It can be anything, but it's a number. And that number has the data which is going to get populated ultimately into EAX register. That is the short of address translation, how address translation works. There are flags here. These are very important flags. A lot of those flags has a lot of information like security information, whether it's a valid page or not. If it is not valid, there will be a page fault, and there will be a page fault handling happens, so on and so forth. We will discuss that part as well. What is the role of CPU? What is the role of operating system? All those things we will discuss shortly. Whenever an instruction like this comes, there will be address translation. If it is pointing to an invalid page, there will be access violation. We will see that in great detail shortly. And if it is a valid page, the address will correctly translate to a valid page inside the RAM. So this is the RAM. The value, whatever value we are trying to read, that value from the RAM will be copied to EAX. All this is done by the CPU. As long as the page is valid, operating system has no role to play. Operating system will come into the picture only if the page is not valid. So operating system is like a police or a cop. So only if there is a problem, they come into the picture. And that's what we're gonna discuss next. One thing worth mentioning is, where is this page table sitting? Page table is also in the RAM. Page table is sitting inside the RAM. So this is the page table sitting inside the RAM in some address. And how CPU knows about the page table? From the CR3 register. So CR3 register is pointing to the root of the page table. It's actually a B tree. I'm not going into the details of it. Why it's a B tree? Because there is a search going on. Because you need to find the virtual address and corresponding physical address. So there is a search. That's why it is organized as a B tree. It is a 3-level B tree inside 32-bit, and it's a 5-level B tree inside 64-bit. And it's a 4-level B tree when PAE is turned on in 32-bit. Don't worry about such details. Let's see what happens in detail when there is no page table entry. That is our next focus right now. So again, we have the virtual address space or the address space right here. There is user mode and there is kernel mode. Now the user mode is divided into pages. In fact, kernel mode is also divided into pages. So we are focusing on user mode divided into pages. 4K pages. So these are all 4K chunks. Some pages are allocated. We call an malloc here, heap alloc, thread stack, some binary loaded. So this is our hello world binary. Hello world binary is, say for example, it's big, more than 4K, so it spans across a couple of JSON pages. This is the hello world binary. And put that in a different color. This is the hello world binary. All the global variables of our hello world application comes inside this. So all the global variables, static variables, so on and so forth, everything is inside this. This is all allocated. Now someone has called a virtual alloc. Virtual alloc is here. This is all the shaded regions are allocated. All of them has a valid page table entry. Now, where is the page table for this particular process? Let me draw that here. So this is the page table. We have seen that page table has 3 columns, important columns. One is the virtual address, physical address, and then the flags. Page table has page table entries. So these are the page table entries. And here is our CPU. CPU has the CR3 register. CR3 register is the root of the page table. In fact, it is pointing to something called page table directory base. Doesn't matter to us. We have the RAM here. This is the RAM. Random access memory, RAM. All the valid pages has corresponding allocations here in the RAM. All the pages which are having corresponding page table entry has allocation inside the RAM. Let's put that thing in. all these allocations map through page table to the RAM. Now our focus is about accessing one of the pages which doesn't have anything here, or it has a page table entry here, but the protection on the flags or some of the rules on the flag is not allowing us to do the operation we are trying to do. Either it's read or write or execute, anything. It could be anything. For some reason, the CPU is not able to translate this particular virtual address to a physical address using page table. That is our scenario. What happens next? Let's write our instruction again. Move EAX, dword PTR 0x12345678. This is the instruction we are trying to read from. This is the address we are trying to read from. That address is coming from this particular page, and this particular page doesn't have a valid page table entry. So there is no page table entry for that particular page, or it has a page table entry, but it doesn't have a valid flag which approves this particular operation. Let's assume that there is no page table entry. That's easier. Now this instruction we have given to the CPU. CPU is trying to process this instruction. We have given the ones and zeros corresponding to this particular assembly statement. We have given the opcode, the operation code in binary, to the CPU. CPU will look at the current CR3 register, get into the page table. Page table is ultimately sitting in the memory. So this is inside memory. This is inside the memory. So this whole thing is inside the memory. This is the page table PT. Using the CR3 register, so it's an address to the page table. It reached the page table and it tried to convert the virtual address to physical address, and it failed. What the CPU does is CPU create or generate something called an interrupt, or in this case page fault. Page fault is nothing but an interrupt. The control get transferred to the operating system interrupt handler, or the page fault interrupt handler. Now let me talk a little bit about interrupts. Interrupts are signals from different parts of the system. What is the significance of interrupt? Interrupt, like the name says, interrupts what the CPU is currently doing. Remember I was telling CPU always execute the next instruction pointed by the EIP register. That is the job of CPU. So EIP register is there, instruction pointer. CPU always execute the instruction pointed by the EIP register unless either we switch off the power to the CPU or an interrupt comes. What happens when the interrupt comes? When the interrupt comes, CPU transfer the handle to the interrupt handler, which is registered by the operating system. And another most important thing about interrupt is always handled in privileged mode. That is the single most important information about interrupt. So interrupt will stop the execution of the EIP. So the next instruction pointed by the EIP register, it will stop doing that, and it will handle the control to the interrupt handler. So the interrupt handler will start executing, and that instruction will be privileged. The interrupt handler is always executed in privileged mode. In short, whenever there is a page fault exception comes from the CPU try to convert the virtual address to physical address using the CR3 register and the page table. It failed for XYZ reason. It created a page fault, and that page fault, that control comes right here to the operating system. It is up to the operating system to decide what to do. Operating system checks a lot of things. Whether that page is in page file, then it'll push it to the memory. It'll do the normal page fault. if it doesn't have a valid page. For example, if you're trying to access a null page or a null pointer, then it will give the control back to the application. It will tell the application, hey, application, you have created an exception. Yeah, I'm giving you one chance, exactly one chance to handle it using your try catch block inside your program. If this instruction, so this instruction was in a try catch, or try except, because if you're using structured exception handling, it could be depends on the programming language. Nothing but exception handling. The program has an exception handling for that particular exception. The operating system ignores this and let the program keep going from the exception handler. Depends on how the exception is handled. This is called first chance. The first chance exception is an opportunity for the program to handle the exception. All the exception we are getting in our programs are first chance exceptions. What is second chance? Now, if the program is not handling or it doesn't have a try catch block, page fault failed, operating system got the handler executed by the CPU, the interrupt handler, the application is informed that there is an exception, but application doesn't have a corresponding handler. Or the user mode thread has a default handler. That handler will get executed. And that is when we see all the signatures of crash. We will see the signatures of crash. And that is what we call second chance exception or a crash of a user mode application. A second chance exception is a guaranteed problem in an application. And what happens if there is a second chance exception in a operating system? That is when we see the blue screen of death. This particular page can be in the kernel as well. We will see when we discuss the kernel. This particular page which we try to access here, which is not allocated, can be in kernel as well. So if it is in kernel, things are slightly different, but more or less the same. It'll see if that thread is handling that exception. If that particular kernel thread is not handling that exception, it'll blue screen the computer. That is when we see the kernel panic or blue screen. So what is a first chance exception? First chance exception is an opportunity for the program to handle it using a try catch. And if the program is not handling, operating system will take over the exception and declare the program as crashed. Coming back to the slides, we have discussed kernel mode and user mode a little bit. Kernel mode, we didn't see any details. We have seen in detail the address translation. So how the address translation works. What happens if the address translation fails? Address translation is done by CPU, not by operating system. Make sure you understand that. And if the address translation is success for an instruction, operating system doesn't come into the picture at all. So operating system has no role to play in an instruction like move ex, dword ptr 0x12345678. Only operating system comes into the picture when there is a failure. If that address is not valid, then OS comes into the picture. Otherwise, OS is out of the picture. It is a business between the application code and the CPU. Now let's have a look at user mode addresses inside the debugger. So again, I'm opening the same executable we've been debugging. If you look at all these addresses are on the range between 0 and 7 follows 7FF. Now, if you want to see a particular address value inside a particular address, we have seen the command DC. This question mark DC0, I'm trying to dump out the 0th address. I'm trying to dereference this particular address inside this particular application. I'm getting this question mark. So this question mark means that there is a failure in the translation of pages. So if I have an application which is trying to access any of these addresses, that application will get an access violation, or there'll be a page fault. Access violation and page fault is one and the same thing. It's just that it is handled slightly different when there is an actual page fault and there is a failure in translation. There is no valid page table entry for this particular page. To get more information about this particular page, the command is bang address. I'm typing bang address 0. It is trying to get information about this first page of this address page. Bang address 0. It can be any valid address if you like. So we will see some valid address as well. So it is saying it is free. There is no allocation whatsoever with that particular address. So it is a free page. And it is page no access. So if you access this particular page, you will get an access violation. That is what it says. Now let's look at a valid address. This is a valid address. Why it is a valid address? Because this is where our binary is mapped. Remember I was talking about the mapping of the binary? This is where it is. This binary is mapped between this address and this address. Let's do a bang address here. We are expecting a different result for the bang address. We have more information here. It is image. Image means that there is a binary loaded into it. It is an image. Most of this information are coming from the flags of the page table entry, especially this one. We have execute copy permission on this particular page. It is a committed page. We'll see what is committed, what is reserved, so on and so forth. And a lot more information about that page because that page is having a valid page table entry. These are the further commands if you want to see what is there in the binary, etc. It is related to a binary, so that is why it's giving you more information. Some of these commands we have seen: lmvm, bang lmi, ln, we have seen all this. And bang dh we have not seen. So bang dh is a command which gives you information about the portable executable. If you're doing some kind of malware analysis, etc., you can see all the information about the different headers inside the portable executable. That is bang dh. Now if I do a G and then if I do a K, and if I take one of these stack variables and if I do a bang address on that, it clearly says that the usage of that particular address is stack. By the way, these are the different buckets of memory, regions, pages inside the user mode address space. We have peb, tab, heap. Heap is the region where if you do an malloc, that's where it goes. Page heap we will discuss when we discuss stack corruption. And these are the other regions which are used for different purposes of debugging and activation context, etc. This particular page is from stack. It is a read-write page. It is giving us more information about this particular stack. If I do a ~0k, it will switch into that particular thread and it'll give you that particular stack. What I recommend you is that do an malloc and do a bang address on the address which is returned by the malloc and see what is the output you are getting in the bang address command. Do that as an exercise. We have seen different types of address in the debugger, and we have seen how an address is looking if that address is not allocated. This is a very important information. That question mark we have seen, it's a very important thing. We will see that a lot in the case of crash. We have not seen any kernel mode, and we can't access kernel mode from the user mode. We need to have a kernel mode debugger. If you try to dump out a kernel mode address, say for example, if I do a DC, again, we will get that question mark. Because this address, anything start with 8 is a kernel mode address, potentially in kernel mode, because that is where it starts. The most significant bit is 1 for all the kernel mode addresses. We get the same question mark.